This is part 4 in the multiple regression series. Now, you learned a lot of information in videos 1, 2, and 3. So the good news is we're going to take a little breather and mostly do review here. So we'll see a new example, tie everything together kind of in order, and also see how, if we have a couple options for models, how we might decide which of them better meets our needs. So our new example is coming from a data set called convenience. So in this data set, each row represents a particular franchise location for a national gas station and convenience store chain. You know, something like Chevron or Shell, where they sell snacks in the convenience store. So we want to predict the sales of the convenience store. We have 3 numeric predictors at our disposal. So there's the volume of gasoline sold at that location on that day, the number of cars washed at that location on that day, and the price of gasoline on that day, right? So should we throw all of these things into our model? Well, remember, we have one thing to do first, which is to double check that none of our predictors are strongly correlated with each other. We do that with the scatter plot matrix. So in JUMP, I'm going to analyze multivariate methods, multivariate. And I'm going to pick all of the numeric variables, including the response variable y. So I've got y, x1, x2, and x3. All right, so a couple things I'm looking for. Remember, we want a linear relationship between y and each x. So it looks like there is a pretty linear positive relationship between the convenience store sales and the volume of gas sold. A weaker relationship between the sales and number of washes, but I don't see any curved patterns, so we don't need to exclude this. And then probably still a weaker still relationship between the sales and the price of gasoline. A little bit of a funky pattern here, but it's not noticeably curved, so we'll keep it in for now. All right, then on my correlation matrix, remember, we don't want predictors, x's, that are strongly correlated with one another, either positively or negatively. So the rule of thumb I gave was we don't want predictors that have an absolute value of their correlation coefficient any larger than 0.7. Okay, so look where the x's in the rows, so the bottom 3 rows, meet the x's in the columns, so the 3 columns to the right. So I'm scanning these numbers and confirming that I don't see any values more negative than negative 0.7 or more positive than positive 0.7, with the exception being the diagonal, because that's where one variable meets itself. Okay, so 0.12, 0.33, negative 0.03. These are pretty weak correlations between our predictors. So we are allowed to use all of them if we so desire. So let's build that model then. And we would call this the full model because we're using the full list of predictors at our disposal. So we analyze fit model. Right, so we're going to predict these sales, it's sales in the convenience store, using all 3 of the numeric predictors. So add all 3 to the model. Now there are a couple categorical predictors in there, the day of the week, and then a indicator variable saying whether it's the weekend or not. We might do some stuff with those next week, but let's make sure we have the basics down with the numeric variables first. All right, so this is the model I want. And one more little thing, I'm going to check this box that says keep dialog open. That'll become evident while we're doing that in a little bit. And now we're ready to run. Okay, so before we start doing all sorts of crazy things, let's check that this model meets the assumptions for multiple regression. So quick reminder, what were those assumptions? Well, there needs to be a linear relationship between y and each x. We had a preliminary check with our scatter plot matrix, but we have a couple more sophisticated ways to check for that. So we will. We need to check for constant variance, normally distributed errors, independent errors, and then there's just this broad assumption that our data it comes from a representative sample from this chain of gas stations. All right, so how do we check for linearity? So we said we already looked at the scatter plot matrix and didn't see any curved patterns where each x met y. The other place we can look, well, one of the other places is on the residual by predicted plot. So the absence of any curved patterns here is a good thing when it comes to linearity. So I don't see any curvature here. So far, so good. And then the last thing we can do is save the residuals and plot them against each x. So to get our residuals for the whole thing, I'm going to the top red triangle, save columns, residuals. Now they'll be in our data table, and we can plot them to get a better look. I'm going to be fitting them against each x. So the residuals will be on the y-axis, and then selecting each of the x's, putting them all in here will give us 3 separate graphs. Right, so we're going to look at each one and confirm that there's no curved patterns. So this one on the left is pretty random scatter. The one on the right, not really any curved patterns. We do have a couple outliers, it looks like, but we have hundreds of gas stations here, so there's always going to be an oddball or two. The price data has a bit of a pattern to it. Now, price is discrete, right? It's to the nearest cent. So that's why we see these kind of vertical streaks. I don't see like a big parabola shape though, or a big arc. So as far as linearity, I think we're all right here. All right, how about constant variance? Nice thing about that is we only need to look at one plot, and we've already got that plot. So we're looking at the residual by predicted plot and verifying that there's not any of those funnel shapes where it gets narrower and spread at one end or the other and fans out on the other side. Right, so the thickness here looks similar across. All right, our third condition, which order did I do them today? Normally distributed errors. So being that we already have the residuals or errors in their own column, let's just make a histogram and a normal quantile plot of those using analyze distribution. All right, so our histogram looks fairly bell-shaped. We do have a tiny bit of a tail to the right. It looks like that's due to the presence of just a couple outliers. We have 283 gas stations, though, so it's not surprising that there would be a couple that are exhibiting some unusual behavior. I'm going to add in a normal quantile plot. And it looks for the vast extent of this, we have a linear pattern. Like we said, a couple outliers, but the confidence bands give us a little bit of room for wiggling around in the tails. So this one looks fine. We don't see any noticeably curved pattern for any large portion of the data. All right, lastly, we're checking for independent errors. So I'm back in my model output. I'm going to go up to the top red triangle, down to row diagnostics, and plotting residual by row. So remember, we want our errors to be uncorrelated. So not showing any positive trend nor any negative trend. So this is good. They just kind of bounce around randomly across the plot, neither ascending nor descending. So we don't see any pattern where the errors might be correlated to time if these were put in the spreadsheet in the order that they were collected over time. Okay, so the assumptions seem to be good. Then we would ask, well, is it a good model or a useful model? Does it help us predict the sales at the convenience store? So we did the test for model utility in video number 3. So recall we have a compound hypothesis here. Actually, let me go a little bigger. I'll just use my stylus. The null hypothesis was that none of our predictors were useful at predicting these sales. So we have this compound hypothesis where all the beta coefficients are equal to 0. So that's beta 1 and beta 2 and beta 3 all equal to 0 versus at least one of beta 1, beta 2, or beta 3 does not equal 0. Okay, so in words, like a verbal hypothesis, the null hypothesis that none of those 3 things, the volume of gas sold, car washes, or price of gas, helps predict convenience store sales. Alternatively, at least one of those things does. So where can we find the test statistic and p-value for that? That is the F-test in the analysis of variance table. Okay, so testing this model, which has 3 degrees of freedom, because remember the degrees of freedom there was k, are the number of predictors. Our F statistic with 3 and 279 degrees of freedom is 71.6649. And the p-value to the right of that value on the F distribution is really, really small. So small p-values reject the null, and we can say we did find convincing evidence that at least one of these predictors is useful at predicting the sales at the convenience stores. All right, and the advantage of that global F-test is we tested them all simultaneously while keeping our type 1 error rate fixed at, say 5%. All right, let's now think about, well, we know something is useful. Is it everything or just some subset? And here we run into the issue of multiple comparisons. That is, now we have 3 predictors to test. So we'd need to do 3 t-tests if we want to look at them all. We could run into some issues with our type 1 error rate creeping up. So let's start a little smaller. Let's start at alpha equals 0.01 for each of these t-tests. So let's think about our first predictor, the volume of gasoline sold. Does that help predict convenience store sales? The null hypothesis is that no, it doesn't. It's not a significant predictor. In which case, the partial slope for the volume of gas sold, beta 1, would be equal to 0. There's no relationship, no linear relationship between those 2 things. Alternatively, there is a linear relationship, so that partial slope does not equal 0. All right. Think for a second, what would the other hypotheses look like? To save time, I'm just going to click and show you. They're going to look very similar. We're just going to change up the subscript. So for car washes, since car washes was X2, that would be associated with beta 2. Price of gasoline was X3, so beta 3. And then in my verbal hypotheses, I would just state those other variables instead of, like we did in the first one, was the volume sold. Okay, so pretty repetitive here. On an exam, I might ask you for one set of these, but I'm not going to ask you for all of them because they're so similar. All right, so how would we find the test statistics and p-values for those sets of hypotheses? they're going to be right below in the parameter estimates table. Okay, so for our test of beta 1 to see if the volume of gas sold is a significant predictor, looking across that row, our test statistic is 13.79, really big. So that's going to be associated with a really small p-value. So it looks like the volume of gas sold is a highly significant predictor of convenience store sales. How about car washes? X2. So the T ratio there is quite a bit smaller, only 1.86. And as such, the p-value is bigger, 0.0637. So if we're using the 1% significance level, we wouldn't consider that statistically significant. And also in this case, we wouldn't add the 5% significance level either. All right, then last, the price of gasoline in gallons. Price per gallon, sorry. So notice there, we see a negative estimate. So what does that imply? Well, there was a negative trend noticed that as the price of gasoline goes up, the convenience store sales go down. Now, we could probably rationalize that. People have a finite amount of money to spend. If they're spending most of it on gas because gas is expensive, they might have less left over for a snack or a less discretionary income. All right, so the test statistic to find out if that's a significant predictor was negative 1.6. So the negative is not hopefully a surprise because the estimate was negative. It just means we're on the other side of the t-distribution, but the t-distribution is symmetrical. The area in the two tails is 0.1103. So that is not significant either, and by a greater extent than the car washes was. Okay. So when it comes to refining our models, remember we like simpler models when possible. If we want to trim the fat here, we're going to go for the factor or the predictor that had the largest p-value first. That would be the best candidate to get rid of because it was the least significant of a predictor. All right, you with me? So let's get rid of the price per gallon. And remember how I said check the box for keep dialog open? That's because this was our previous model, and now we can tinker with it. So say we want to get rid of price per gallon. You can either double click on it here, or you can highlight it and press remove. All right, so let's try fitting a new model with just the volume and the number of washes. So all you have to do once you get rid of X3 is press run again. So this is going to fit the new model, and the results will be in a new window. So notice it's called Fit Least Squares 2, whereas my original was Fit Least Squares. Because depending how many times you edit your model, you could end up with lots of windows, but at least it's going to label them in order. So just be careful which screen you're looking at. So let's look at the new one, number 2. Now, is this model useful? Let's look at the f-test. Here we go. So again, a very large F ratio, a very small p-value. So this is a useful model. Then let's look closer. Volume still has a large T ratio, still has a small p-value. So volume is still a highly significant predictor of the sales at the convenience store. Washes, this is interesting. Washes became slightly more significant in this model. Let me see if I can side by side. My computer thinks it's smart here. All right. So in the foreground is the first model with x1, x2, and x3. So in that context, the washes had a p-value of 0.0637. So they weren't statistically significant at the 5% level there. However, once we take away the price per gallon, that result changed. The result for the volume changed as well. That one actually became more significant in this model. So this is why when we do those interpretations, like when we say that volume is a significant predictor of sales, we put on those caveats that, well, when used in conjunction with these other variables, because the results sometimes can change. Okay, so washes is now a significant predictor of sales at the 5% significance level. If we had said, well, we wanted to use the 1% significance level to limit the rate of type 1 error, then I guess we would fail to reject this null hypothesis. But it may still be worth leaving this in the model. You don't have to get rid of predictors just because they're not statistically significant, because they will improve the predictions a little bit at least. Maybe not so much that you can be convinced that it's a true relationship, but the fit does always increase the more predictors you have. All right, so let's look at our measures of fit and compare and contrast these two models that we've constructed. So I've got them side by side here for you. All right, now remember R squared, plain old R squared, is the proportion of variability in Y that we've explained with our model. So is either model, vastly superior for R squared? Well, on the left, we have 0.435. On the right, we have 0.430. So pretty close. The adjusted R squared, remember, imposes a small penalty for each additional predictor in the model. So the penalty is going to be greater on the left because we have 3 predictors than it is on the right where we have fewer. So R squared adjusted, 0.429 on the left, 0.426 if we round to 3 decimal places on the right. So they match for the first 2 decimals, and then they're just a hair off for the 3rd decimal place. So these are awfully close to one another. The one on the left does do a just so slightly better job at predicting, but if we think in terms of data collection, if this company is trying to minimize their use of resources in collecting this data, wouldn't it be nice to only have to find 2 pieces of information for each location instead of 3? So you could say there's a benefit there that the reduced model is going to make it a lot easier to collect the data that they need. All right, one last way that we can compare the 2 models would be with their root mean square error. So recall, this is the typical error of a prediction. So on the left, this is about 245, almost 244.99. So that would be in the units of Y. So this is dollars. Based on knowing volume, washes, and price of gas, our predictions usually get to about $244.99 away from the actual result. On the right, it's slightly higher, $245.67. Okay, but we're still within $1 out of $245, so that's still pretty close. Okay, so which one is better? They're really close. And if collecting your data is costly or burdensome, that each franchise owner has to calculate and report each metric, um, you really don't lose much predictive power with the model on the right. So it's a pretty efficient and lean model. The one on the left, a little bit more complex, has one predictor in it that wasn't especially close to being a significant predictor, but if we include it, we can eke out just a little bit better predictive power. All right, so if you did decide to go with the model on the right, it's a new model, so you'd have to recheck those assumptions just to make sure that taking out the price of gas didn't cause any weird patterns to appear in your residual plots. So looking at the residuals against each x that's remaining, no weird curved patterns, no curved patterns on the residual by predicted plot, and no funnel shapes either. So we also have constant variance being reasonable. The residuals still look normal for almost all of them. We do have a couple outliers still. And then finally, there doesn't seem to be any correlation among the errors. They just randomly bounce up and down throughout the rows. Okay. So this model, if we went with the reduced model, we could find our prediction expression using these estimates that remain here. And then being careful not to extrapolate, we could make predictions based on a certain volume of gasoline that's sold and a certain number of car washes. All right, so that does it. If you're in my spring 2020 Statistics 2 class, you are now ready for homework number 10. After homework number 10, we'll get to slightly more complex models where we can look at categorical variables and a few other things that you've never even heard of yet. Okay, so I'll see you in installment number 5, but perhaps not for a little while yet.